So when you think of Greenland, what comes to mind? Probably just a huge, endless sheet of white, right? But have you ever started to wonder why? Why is this one island buried under such a massive ice sheet? Well, the answer is this amazing story that mixes geology, ancient climate, and just some really cool physics. Let's get into it. Okay, get this. A staggering 80% of Greenland is covered by ice. Now, you might think, well, it's way up north, of course it's icy. But that's not the whole story. Not at all. I mean, think about other big land masses at similar latitudes, like Scandinavia or parts of Siberia. They're not buried in ice like this. Something completely unique is going on in Greenland. So, that brings us to the big question for this explainer. What is Greenland's secret? Turns out it's not just one thing. It's this powerful combo of three key factors: the actual shape of the land under the ice, a really dramatic climate shift that happened millions of years ago, and, believe it or not, a set of processes that let the ice sheet basically keep itself alive. We're going to break this down into four parts. First, we'll look at the foundation, this sort of geological bowl that's holding all the ice. Then we'll talk about the climate switch that got the whole thing started. After that, we'll check out the engine that keeps it all running. And finally, we'll look at the edges of the ice to see how it all stays in balance. All right, first things first, let's talk about the foundation. Long before there was any ice, there was just land. And the shape of that land is the first and maybe the most crucial piece of this whole puzzle. So here's the wild thing about Greenland's bedrock. It's not a mountain peak in the middle. It's actually a giant bowl. You've got this ring of super high coastal mountains, kind of like the rim of a huge saucer. This rim acts as a natural wall, basically holding all the ice in and stopping it from just sliding out into the ocean. But why is the center so low? Well, there's a process for that, and it's called isostasy. The weight of all that ice, we're talking over 2 quadrillion tons, is so ridiculously heavy that it has literally pushed the Earth's crust down into the mantle. It's sunk the middle of the island by up to 800 meters. The ice actually created its own deep container to sit in. Okay, so we've got the perfect geological bowl. But what filled it up with all that ice? For that piece of the story, we've got to rewind the clock a few million years to a massive climate shift that basically flipped the on switch. The ice sheet as we know it today really got going somewhere between 3.6 and 2.4 million years ago. Before that, during a period called the Pliocene, the climate was a lot warmer and Greenland only had some smaller glaciers. But then, some major tectonic shifts started changing up ocean currents and airflow, setting the stage for a planet-wide deep freeze. But the real tipping point was a huge drop in atmospheric CO2. It went from around 400 parts per million down to below 280. And that was it. That was the magic number. The summers just got cool enough that the winter snow didn't completely melt away. It started to stick around, year after year, building up for centuries until this continent of ice was born. Now, once the ice sheet was there, it didn't just passively sit around. No, it started to actively create its own cold environment. It essentially built its own engine, a really powerful self-cooling system. The first part of this engine is something you might have heard of, the albedo effect. It's actually a pretty simple idea. Dark surfaces absorb heat from the sun, and light surfaces reflect it, while the bright white surface of the ice sheet is like a giant mirror. It reflects most of the sun's energy right back into space, which creates this powerful refrigerator effect for the whole region, keeping Greenland cool. And just look at the difference here. Ice and snow bounce back a massive 80 to 90% of the sun's radiation. Now compare that to the land and the ocean around it, which reflect less than 20%. That huge difference in reflectivity is absolutely key to the ice sheet's survival. The second part of the engine is just as mind-blowing: its own height. The ice sheet is over 3 kilometers thick in the center. I mean, just try to picture that. It's an ice mountain. Its surface is so high up in the atmosphere that it creates its own permanent, high-altitude, cold climate. It's basically a cold desert up there where it almost never gets above freezing. The ice sheet literally holds its own summit in a constant state of deep freeze. So if the ice sheet is so good at keeping itself cold and preserving itself, why doesn't it cover 100% of the island? Why is there still that 20% of green, ice-free land? Well, the final piece of our story is right there at the margins, where this dynamic balancing act is always happening. See, down at the coast, the elevation is much lower, so the air is a lot warmer. This creates what scientists call ablation zones. It's just a fancy way of saying these are areas where more ice and snow melt in the summer than what gets added in the winter. On top of that, where the glaciers actually meet the sea, they break off into these huge icebergs. That process is called calving, and it's this combination of melting and calving right at the edges that defines the ice sheet's boundaries. I think this analogy from our source material just sums it all up perfectly. Imagine Greenland as a heavy ceramic bowl. The mountains are the high edges that keep the ice from spilling out, and the white, icy surface reflects the light, making sure everything inside stays frozen. It's such a simple but really powerful way to picture this whole system. So let's recap the whole thing using that analogy one last time. The geology is the ceramic bowl itself, the container. The ancient climate shift, that was the moment we placed the bowl in the freezer. And those feedback loops, the albedo and the elevation, they're like the bowl's white reflective surface, making sure it stays perfectly cold. So in the end, the Greenland ice sheet isn't just some static block of ice on a map. It's this incredibly complex, dynamic system. It exists because of a true perfect storm, this unique intersection of geology, a critical moment in climate history, and some really powerful, self-reinforcing physics. And really, that's the main takeaway here. It's only by understanding all of these interconnected pieces, the bowl, the switch, and the engine, that we can really start to appreciate the true nature of this vast, critical, and constantly changing feature of our planet.